Okay, so we are going to go through section 10.3 today. So 10.3 is the cross product of two vectors. So our objectives for this lesson, we're going to find cross products of vectors in space. We're going to use geometric properties of cross products of vectors in space, and we're going to use the triple scalar products to find volumes of parallelepipeds. So the cross product. So if you look at the box down here, so if we're writing our vectors in standard form where we have the I component, the j component, and the k, if we take two different vectors, so three-dimensional vectors, the cross product is going to be multiplying. So if we think of I right here, it's not using the coefficients that are with I, it's taking the coefficients u2 times v3 minus u3 times v2. So multiplying those values. Minus, so then if we go to j, so we're not going to use j, it's going to be u1 times v3 minus u3 times v1. Plus, then we're going to take the k values, so we're going to not use those. We're going to take u1 times v2 minus u2 times v1. So this hopefully kind of looks familiar, like when we were doing matrices, thinking of the 3x3 matrix and finding the determinant. So we are going to use that idea of the determinant. We're not technically finding the determinant, but we're using that setup to find the values that we're looking for. So this goes back to our matrices. So if we put the I, the j, and the k here, here's our coefficients for vector u, and here are our coefficients for vector v. So if we are trying to find, so you remember we block out the row and the column with I, so then we take the u2 times v3 minus u2, or u3 times v2. So that's where that smaller 2x2 matrix comes from, this one right here, and this one right here. And then we'll notice this is the same thing that we just saw on the previous slide, but sometimes if you're thinking about it as the determinant, like we've already done, it helps you remember what you're multiplying, what you're subtracting, to find those values. So this is the determinant of that smaller matrix. It's going to give you that value. It says to note the minus sign in front of the j component. So if we go back to the previous slide, so this is positive minus the j value plus the k value. Okay, so example 1, given that u is I plus 2j plus k, and v is 3i plus j plus 2k, we're going to find each cross product. So for A, we're going to take, so we have I, j, k up here. These are our coefficients of I, j, and k. So for u, it's 1, 2, 1. And then for v, it's 3, 1, 2. So that's where that matrix is coming from. So if we block out the I row and column, we're left with that smaller matrix, the 2, 1, 1, 2. That's where that's coming from right here. Minus, oops. Let's go back. Okay, minus, if we block out the j row and column, it's 1, 1, 3, 2. And then plus the k, so we block out that, it'd be 1, 2, 3, 1. So we're going to find each of these determinants. So if you think about how you find the determinant of a 2x2, we're going to take 2 times 2, which is 4, minus 1 times 1, which is 1. So this would be 4 minus 1. This would be 2 minus 3, and this would be 1 minus 6. But keep in mind that this is minus right here, so that's going to change the sign. So we have 4 minus 1 minus 2 minus 3 plus 1 minus 6. So those are what we just talked about on that previous slide. So that would turn into 3i plus, because this is going to be minus 1 and it's minus a negative 1, so that would be plus j minus 5k. Okay, so B is the opposite. So we just did U cross V, now we're going to do V cross U. So that just changes where we put the numbers. So these are the components of V, and these are the components of U. So we're going to do that same thing, come up with those 2 by 2 matrices. Notice, again, that's minus right there. So this time it's going to be, instead of 4 minus 1, it's going to be 1 minus 4. And then this is going to be 3 minus 2, and this is going to be 6 minus 1. So you'll notice it's going to switch the order of all of these values that we have up there. So that results in negative 3i minus j plus 5k. So it says to note that this result is the negative of the part in A. So when we did u cross v, we got positive 3, positive 3i, positive j, and negative 5k. So this is going to be the opposite. So then our last one is v cross v. So you'll notice these are the same numbers, okay, for v and v. So if we were to do that, you end up with 0. So if you're taking a vector and crossing it with the same vector, it's going to result in 0. So from that example 1, we found that u cross v is equal to the negative of v cross u, and v cross v is 0. So here are some other other properties of cross products of vectors. So this is the one that we just found, okay? If you have u cross the sum of v and w, this is going to kind of look like the distributive property. So you can take u cross v plus u cross w. So those would be equivalent. If you have a scalar number times the cross product, you can take the scalar times the first vector and then cross it with v, or you can take the first vector and cross it with the scalar times, or scalar multiplied by the second vector. We know that u cross u is 0, just like v cross v was equal to 0. If we cross a vector with a 0 vector, it's going to equal 0 as well. And then if we have a dot product, so remember we learned the dot product, if we have the dot product of a vector and a cross product of a vector, you can kind of use that associative property. So we can do the cross product of u and v and then take the dot product of w, and those will be equivalent. Okay, so some geometric properties of the cross product. So we learned that if we switch the order, then it's going to be the negative. So that means that it's not commutative. So if you remember our simplest version, commutative means like 3 plus 2 is equal to 2 plus 3. So we know that cross products are not commutative because they do not equal each other when we change the order. So in particular, its property indicates that the vectors u cross v and v cross u have equal lengths but opposite directions. Okay, so some other geometric properties. So if u and v are non-zero vectors and theta is the angle between u and v, u cross v is orthogonal. So remember, orthogonal means at a right angle, at a 90-degree angle, to both u and v. And we'll look at a picture of that in an upcoming slide here. The magnitude of u cross v is equal to the magnitude of u times the magnitude of v times the sine of the angle between them. U cross v is equal to 0 if and only if u and v are scalar multiples of each other. So remember we just talked about in a slide ago that u cross u is equal to 0 and v cross v is equal to 0. So that's also going to be the case if they are scalar multiples of each other. And then the magnitude of u cross v is equal to the parallelogram having u and v as adjacent sides. And we're going to use that in our last problem today. Okay, so both u cross v and v cross u are perpendicular to the plane determined by u and v. So here's a plane. So one way to remember the orientations of the vectors u and v and u cross v is to compare them to the unit vectors I, j, and k. So k would be equal to I cross j. So if you think about that here, that's going to create that 90-degree angle. Okay, so example 2, we're going to find a unit vector that is orthogonal to both of these vectors. So first of all, before we can find the unit vector, we can just find the cross product, which we know will be orthogonal to both of these vectors. It will be a 90-degree angle with both of these. So the first step is to find the cross product. So we're going to set this up. We have 3, -4, 1 as our u vector, and we have -3, 6, and we have no k value, so that'd be 0. So that's where those numbers are coming from. Here's a picture, so we know that we're finding, so here's u and here's v, and this u cross v is, you can see, is at a 90-degree angle to both of those individual vectors. Okay. So if we find the cross product like we did on example 1, so doing the same sets, finding those individual 2x2 determinants, you would end up with -6i minus 3j plus 6k. So this right here is the cross product, so this is this vector right here. But this problem is asking us to find a unit vector. So if you remember back to when we did vectors in the previous chapter, you're going to find the unit vector by taking the vector and dividing it by its magnitude. So the magnitude, we're going to take each component, that -6, -3, and 6. So we're going to square those, add those together. We get 81. So the square root of 81 is 9. So now what we have to do is we're taking this -6, the -3, and the 6 and dividing that by the magnitude. So the cross product divided by the magnitude. So if we take -6 divided by 9, we get -2/3. If we take -3 divided by 9, we get -1/3. And if we take 6 divided by 9, we get 2/3. So that's where that resulting, so this right here was the unit vector that's orthogonal to both vector u and v. Okay, so we could have used the cross product v cross u, so to do this, the previous problem, that would also form an orthogonal to both u and v. So with that choice, we would have obtained the same answer, but it would have been in the negative, but it still would have met the requirements of being orthogonal to the two original vectors. Okay, so now we're going to do the triple scalar product. So the triple scalar product, it's saying we have vector u, so here's vector u, vector v, and vector w. So the triple scalar product is given by taking vector u and the dot product of vector u and the cross product of v cross w. So when the vectors u, v, and w are not in the same plane, we're going to use this triple scalar product to determine the volume of a parallelepiped. So a parallelepiped is a polyhedron where all the faces, so every side, is a parallelogram. So think of kind of like a rectangular prism, but stretched on its side. So u, v, and w are adjacent edges. So you can see right here, this is u, this is w, and this is v. And so we find that triple scalar product to find the area of a parallelepiped. Okay, so the volume is going to be the absolute value of, again, the dot product of u with the cross product of v cross w. Okay, so here's our last example. We're going to find the volume of the parallelepiped that we see right here, having u, v, and w as adjacent edges. So you can see that each of these vectors has the starting point at 0, 0, 0. So that tells us that we can take these coordinate points and we can actually turn them into the component form of our vector. So vector u is going to be 3, -5, 1. Vector v is 0, 2, -2, and vector w is 3, 1, 1. And we can do that again because it's starting at that 0, 0, 0 point. Okay, so here is u and v and w. So what you're going to do is we're thinking of how, so when we take the dot product, we're taking the value times. So in this case, we're going to take our u coefficient here, our u values, 3, -5, and 1, 3, -5, and 1, and we're multiplying them by the determinant that we get from doing the cross product of v and w. So if we see here, the 2, -2, 1, 1 is coming from, if we block out that row and that column, this smaller matrix right here. Then if we, so this for our middle matrix here, it's the 0, -2, 3, 1, and then 0, 2, 3, 1 for our last one. So this would be 2 minus -2, so it's going to be 4. This would be 0 minus -6, which is 6. This would be 0 minus 6, which is -6. And then we have 3. This is minus a -5, so that's +5, and that's for the 1. So if we multiply this out, or multiply and then add, we get 36, which means that the area of the parallelepiped would be the absolute value of 36, so 36. So that is it for section 10.3. If you have any questions, let me know, send me an email, and I can help you. Thanks.